Thank you for the introduction. I'm Takashi from NTT, and today I will talk about quantum cryptography. And this is joint work with Amit, Giulio, Tomoyuki, and Kema. So this is a talk about quantum cryptography, but let me start from talking about classical cryptography. Usually, classical cryptography is based on some average case hard problem. And usually those problems have the following properties. One, it is easy to generate a hard instance. And second, the solution already exists. And third, it is hard to find a solution. So these are the criteria about the average case hardness problem that underlie the cryptography. The most basic example of such an average case hard problem is a one-wave function. So it is simply a function that is easy to compute but hard to invert. So the function f takes x as input and output y, but given y, it is difficult to find x such that f of x is equal to y. So because this problem is a search problem, because we are requiring to search for the x, so this is the average case hard search problem. Another basic average case hard problem that is related to cryptography is what is called EFID. EFID consists of two distributions, D0 and D1, and we require the following three properties. First, E, efficiently sampleable, meaning that each distribution, D0 and D1, are efficiently sampleable by using efficient classical algorithm. Second, F means that statistically far, meaning that D0 and D1 are statistically far apart. So if you are given unbounded time of computational power, you can tell apart. The third I means that is computationally indistinguishable, meaning that the distinguisher is computationally bounded and it has only polynomial time computation power, then it cannot distinguish D0 and D1. And the pair of distributions that satisfy these three conditions are referred to as EFIDs. And in this problem, we are thinking about the decision problem to distinguish D0 and D1. So this is the basic form of average case hard problem, hard decision problem. And in fact, in the classical cryptography, it is known that one-wave functions and EFIDs are equivalent in terms of their existence. And moreover, all of classical cryptography, including encryption, signatures, commitment, and everything, imply those two. And also it is known that the existence of one-wave functions or EFIDs implies some of the useful cryptography, like symmetric key encryption, commitment, signatures, and so on. And so in classical cryptography, the world where one-wave function exists is often referred to as Microcrypt, because this is the minimum of obtaining a useful cryptography. Okay, so I finished reviewing. So there's one more about the classical. So let me briefly explain why they are equivalent EFI and one-wave function. Especially, let me focus on how to construct one-wave functions from EFIDs. So suppose that we have EFID. So we have two distributions, D0 and D1, and I explicitly write X as a random that is used for sampling these distributions. Then, by using this, we consider the following function. On input X, which is regarded as a randomness for the sampler for D1, the function f outputs D1 of X. Then, we can show that this is a one-wave function, because if we can invert this function, then if y is given as a sample from D1, then you should be able to find the corresponding X. But if that y comes from the distribution D0, then there shouldn't exist a corresponding X with high probability, so you can distinguish D0 and D1. Now here, it is very important that we can de-randomize the sampler for distribution D0 and D1, and by explicitly treating X as an input. And this is why this connection is possible in the classical cryptography. Okay, let's move to the quantum cryptography. So let's consider something similar in the quantum setting as well. So quantum cryptography is also often based on average case hard problem, and we have similar criteria. So it is easy to generate a hard instance, and solution always exists. And the third condition is slightly different because the instance may be now quantum, so we are giving many copies of the instance to that battery. But that is, except for that, that's the same. It is hard to find a solution given many copies of them. And let's see the example of such a problem. And as a direct analog of one-wave function in the quantum setting, the concept of one-way stage generator was introduced. And it is a quantum algorithm G that takes the classical input X and outputs some quantum output rho. And the problem, and it requires that given many copies of output rho, it is difficult to find X such that G of X equal to rho. And so this is just a direct translation of the one-wave function to the quantum output setting. However, here is a slight definition issue in the quantum setting that it may not be feasible to verify G of X equal to rho, even if we are giving X and rho, especially when rho is a mixed state. So the actual definition involves one more algorithm, which is a verification algorithm. So verification algorithm takes rho and X, and if they're consistent, it outputs accept, and otherwise output reject. Then, and then the hardness we require is given T copies of rho, it is hard to find X such that verification on X and rho accept. This is a one-way state generator. This is just a direct analog one function in the quantum setting. Next, I will introduce EFI. So this is very similar to EFID, which I introduced before. And the only difference from EFID is that we consider the pair of quantum states rho 0 and rho 1 instead of the distribution D0, D1. And the requirements are very similar. We require the three property EFI. So E is efficient. We can efficiently generate the state rho 0 and rho 1, and they are statistically far, but they are computationally indistinguishable against computationally bounded polynomial time adverbs. And also, let me introduce another variant of EFI, which is called QEFID. And that is the same as EFI, except that now we consider distribution D0 and D1 instead of state. Then you might wonder what is the difference from the classical EFID. But the difference is that we now allow the sampler of the distribution D0 and D1 to be quantum. And except for that, that's exactly the same as the classical EFID. Okay, so in the classical setting, I said that one-wave functions and EFIDs are equivalent. Then the natural question is, can we prove something similar in the quantum setting? That is, can we show the equivalence between one-wave state generators and EFI? And if you recall how we derive one-wave function from EFIDs, it was important that we can de-randomize the sampler for the distribution D0 and D1. But now we are considering EFI, which is a purely quantum process, and there is no way to de-randomize the algorithm. As a result, the same approach as in the classical setting doesn't work to show the equivalence between one-way state generator and EFI. But still, there is some non-equivalence if we relax the one-way state generator to have inefficient verification. So if you recall the definition of one-way state generator, that consists of the two algorithms G and V, and we require both algorithms to be efficient by default. But if we relax the requirement to allow the verification algorithm V to be inefficient, which is referred to as IV one-way state generator, then we can show the equivalence between EFI and IV one-way state generator. And this was presented on the first day of this conference by Butler Jane. By the way, in that work, they call it SV one-way state generator, but the same as IV one-way state generator. And also, because QEFID is simply a special case of EFI, so existence of QEFID implies EFI. And also, IV one-way state generator is a relaxation of one-way state generator, so one-way state generator implies IV one-way state generator. But still, there were some missing directions. For example, can we get one-way state generator from IV one-way state generator? And second, can we get one-way state generator from QEFID? And actually, so if we can get that one, then we can also get this one because we can go. Okay, so right now the landscape of the quantum cryptography looks like this. Essentially, all of the quantum cryptography, except for some information theoretical ones such as QKD, any quantum cryptography that requires complexity-based assumptions imply some of those assumptions. And the word where those primitives exist is referred to as microcrypt, because that is below minicrypt where classical one-way function exists. However, we still don't have an equivalent theorem among those microcrypt primitives. So this is our main question. Is all of microcrypto equally minimal? If not, what is the minimal assumption in microcrypt, which implies quantum cryptography? And in this work, to tackle this question, we consider the following classification of microcrypto problem. So usually, microcrypto primitives are of this form. Their average case hard problem with quantum instance law and classical solution X. And as I said, they satisfy these three conditions: easy to generate a hard instance, solution already exists, and hardness given many copies. And here are many examples. But we observe that some of the microcrypto primitives satisfy one more condition, which is easy to verify given solution. Sorry, easy to verify solution given some witness. And an example of such a easy verification variant of the microcrypto primitive is a one-way state generator. And we also have some others which I don't explain in the talk. So we want to ask the question if there is any inherent gap between these two types of microcrypto problems. So in other words, does efficient verification come for free in microcrypt? And I remarked that in the classical cryptography, it is true. Even if we start from some primitives that doesn't have efficient verification explicitly, we can add efficient verification, so they are equivalent. But in the quantum, we don't know if that is true. And in this work, we give some negative evidence about this equivalence. Okay, so let me explain our main results. So our first result is a separation of one-way state generator from QEFID. That is, intuitively speaking, it means that we cannot construct one-way state generator from QEFID. And as QFID imply some other primitive like EF1 puzzle, and one-way SG is implied by something other like PRS. So this means that those primitives cannot be constructed from those primitives. And importantly, they are inefficiently verifiable and they are efficiently verifiable. So this result means that there is a gap between efficient verifiable things and inefficient verifiable things. And yeah, so we cannot get that one, those one from those one. And our, sorry. So there are two concurrent works that show some similar results for this. And our second result separate private quantum money from QFID. And though I don't explain what is the private quantum money, sorry, but they are also efficient verifiable type problem. So this again shows that a gap between inefficient verification and efficient verification. And so our result shows, this picture shows our result. So those represent the microcrypt primitive, but our result gives divide the microcrypt into two categories. One is efficient verifiable microcrypt, and the other is inefficient verifiable microcrypt. And what we showed is that we cannot go to the efficient verifiable region from the inefficient verifiable one. And so this means that the inefficient verifiable one is, especially EFI, should be the minimal assumption for quantum cryptography. So this is the main message, conceptual message about our result. All microcrypt primitives are minimal, but some are more minimal than others. So in the rest of my talk, let me explain some techniques, especially focusing on the separation of one-way state generator from QEFID. So for showing such a separation, we want to construct a unitary oracle relative to which QEFID exists, but one-way state generator does not exist. And for proving such a separation, the typical technique is what is called two-oracle technique. In this technique, we consider the following two oracles. The first oracle is hardness oracle. In this context, this hardness oracle ensures that there exists QEFID. And the second oracle is inversion oracle. And in this context, this inversion oracle breaks any construction of one-way state generator. Considering the world where we have these two oracles, we have QEFID because of hardness oracle, but we can break any one-way state generator, and so one-way state generator doesn't exist because we have inversion oracle. So let me explain how to construct such oracle. So I will mainly explain how to construct hardness oracle to get QEFID, and the main idea is to consider the following oracle, which we call S oracle. So consider to sample a uniformly random subset S of lambda bit strings that doesn't contain all the strings, and it has size to be lambda over 2. Then we consider the following unitary. The unitary swaps all the string basis state and the uniform superposition over all strings that belongs to the subset S. And all the other orthogonal states the unitary acts as an identical map. And this unitary can be written in that way, where S minus is a state defined like that. So this is a very simple unitary that just swaps 0 to the lambda and the uniform superposition over all string of S. And what we actually consider is a controlled version of that oracle, meaning that we have additional 1 qubit that controls if we apply that unitary or not. And so this is exactly the hardness oracle we consider. And let me explain some basic practice about the S oracle. First, we can extract the S minus state from the oracle. That is, given no input, just by making access to the oracle, we can generate arbitrarily many many copies of S minus. And second, we can simulate the oracle if we are given sufficiently many copies of S minus state. That is, for any algorithm A that is given oracle access to the S oracle, there is an algorithm A tilde that doesn't have access to the oracle, such that if A given the input to low and the access to the oracle outputs some state, then A tilde given a low and many copies of S minus but no oracle access can simulate the output of A on the input low, and also it can preserve the additional T copies of the S minus. So essentially, what this means is that, computationally speaking, the power of the oracle, S oracle, and getting many copies of S minus equivalent, because we can simulate oracle by using many copies of S minus, and we can get many copies of S minus using oracle. So based on this observation, we construct QEFID using the oracle as follows. So we consider this construction. So D0 is just a uniformly random distribution over lambda bit string. And D1 is a uniformly random distribution over the subset S. And they are statistically fast because S is a sparse subset. So recall that S consists of 2 to the lambda over 2 strings. And so what we have to show is that the samples from D0 and D1 are indistinguishable against distinguishers that have the oracle access to the S oracle. But as I explained, the oracle can be simulated by using many copies of the S minus state. So this means that we only have to show the indistinguishability between D0 and D1 against a distinguisher that additionally take many copies of S minus, but not the oracle access to the S oracle. So essentially, what we have to prove is the following statistical indistinguishability. The first distribution is the uniformly random element S of the subset S along with the T copies of S minus, and the other is a uniformly random string U along with the T copies of S minus. And intuitively speaking, this information theoretically holds because given T copies of the S minus, if T is just polynomial, then it doesn't have enough information about exponentially large size subset S, and in that case, we cannot distinguish the uniformly random element of S and the uniformly random element over the whole range. And because this is just an information theoretical statement, so this holds under any additional oracle, as long as the additional oracle is independent of the subset S. Okay, so this explains how we get hardness oracle and how to get QEFID under that hardness oracle. And next, I will briefly explain how to get inversion oracle. And simply, inversion oracle is actually just a QP space oracle that does any quantum computation that can be done using a polynomial space. And as I mentioned, the hardness of QEFID holds even if we are given any powerful additional oracle. So the additional oracle doesn't affect the security of QEFID. So what we have to prove is that there does not exist one-way state generator under this oracle. So we have to show that we can break any one-way state generator using such an oracle. And in this talk, I will omit the detail about how to do that. But the idea for doing that is based on the general search of Aronson, which underlies the shadow tomography and the S oracle emulation, which I already explained. So that we can simulate the oracle by using the many copies of the S minus state. Okay, so this is a summary of my talk. And so we showed we propose two categories for microcrypt primitive. One is efficient verifiable and inefficient verifiable, and we show several separation between these two words. And this is in my talk. Thank you for your attention.